And well, we need another problem to solve. And this is quite unusual problem. And as we can read the statement of the problem, the things will take a shape so that we will be able to understand this problem and solve it. So the statement of the problem is a planet in the shape of an ellipsoid. That's right. Consisting of an incompressible fluid. That's also right. Rotates around its axis with an angular velocity omega. Well, there can be some axis, I'm not quite sure. The mass of the planet is m. The semi-axis of the ellipse are of lengths r1 and r2. That is, the distances from the center of the planet to the equator and to the pole are r1 and r2 respectively. Equator and the pole, r1 and r2. And r1 is r1 by r2 is very much less than 1. That means we can consider it approximately spherical, though it's an ellipsoid, but we are free to use its spherical shape in case we will be needing. So write down the equation of locus of equipotential surfaces. And you can see this is hard to understand what they want to solve us. But let us try. I'm first trying to draw an ellipsoid that will not be able to, but I have drawn one. Consider it as an ellipsoid, though it looks like a spherical body. And I will get those semi-axes as x and y. And well, it can also be done. And that's right. And I would like to take this radius as r2 and this radius as r1, because it was given in the problem that r2 and r1 are distances from the center of the planet to the equator and to the pole. So my choice is good. And the planet is also rotating around its axis. So I will take this axis as axis of rotation, and I have put an angular velocity there. That means it is rotating with a constant angular velocity omega around about this axis. And I'm going to read this statement of the problem again, and that this says the mass of the planet is capital M, the semi-axis I mentioned, and write down the equation of locus of equipotential surface. So I'm going to do one thing. I'm going to shift to a non-inertial frame of reference, rotating together with the planet with the same angular velocity omega. I'm going to talk in a rotating frame of reference, and in this frame a centrifugal force will also be acting, and that will be the centrifugal force. And I need to think about the potential energy. So potential energy of the elements, fluid elements of the planet. So I thought about some element placed here. Some element placed here. Yeah, I called it, its mass is delta m or dm, whatever. And I would like to call it x-axis and y-axis. Y-axis is our axis of rotation. So its coordinates becomes x and y in this axis in the plane of rotation. And now I'm going to think about the potential energy. You can see here the potential energy of any element of fluid with mass delta m lying on the surface of the planet and having coordinates x and y is made up of potential energy in its potential energy related to its field of gravity, gravitational field, and I would like to call it UG. And the potential energy of related to the centrifugal forces. Well, centrifugal forces are conservative, I know. So I can also relate a potential energy related to the centrifugal force acting on a fluid element, and I would like to call it UC simply. So there are two kinds of potential energy related to two different forces, the force of gravity and centrifugal forces I can see here. And it was given that something like given R1 by R2 is less than 1. That means I'm taking this ellipsoid looking planet. I'm considering this ellipsoid looking planet as a spherical one, so that I can write its potential energy, and its role has been gone. So I can work now without problem statement, and I'm going to work it. So to write the potential energy, gravitational potential energy, I can simply use it as a spherical, almost a spherical, and this will be simply written as minus G m1 m2 divided by distance of the problem from the center of this sphere, and that is going to be under root x square plus y square. This is the gravitational potential energy, and that can be written. And for its potential energy related to the work done by centrifugal force, we can simply write at UC. That will also be equal to minus m omega square x square by 2. This is m omega square x dx. Yeah, I can write its potential energy as delta m omega square x square by 2. If you have previously solved the Irodo book, you have found this. Perhaps you have found this expression already. If not, do this again in the section of problems related to work energy and energy conservation. You will find a problem related to the work done by centrifugal forces that describes it as a after solving the problem, you will reach to the results obtained here, used here, and those results will tell you that you should treat the centrifugal force as a conservative force, and it can work, and its work done can be written in this manner. And now I need to focus on some other things. Since all points lying on the surface of the planet are stationary in this frame, in our frame, that is the rotating frame, fixed with the this rotating planet, all planets lying on the surface of the planet are stationary, and therefore have the same they will have the same energy, and that means the sum of UG and UC, gravitational potential energy and potential energy related to the centrifugal force, is a constant for any x and y. And this is what we call it an equipotential surface. So we are simply going to get the locus of this equipotential surface, writing like the sum of potential energies, that is G delta m divided by under root x square plus y square, and another one minus delta m omega square x square by 2, and that is going to be a constant. Yeah. And that means we can also write the equation. We can also write this equation in some other form from the given values, and the condition of the problem already informed us or told us that at x equals 0, or you can see the picture, at x equals 0, y is equal to r1. At x equals 0, y is equal to r1. And after putting this value, we can get the constant as well. And the value of constant, if I like the c, so you will get c equal to minus g delta m by r1. Put this value of constant in this equation, and we can also put another information, but we don't need to. Just simply put this value of constant in this equation, and you are going to get the equation like this: minus gm 1 by r1 minus 1 by under root x square plus y square, and from the right hand side you will get omega square x square by 2. After putting these values of and manipulating, you will get this equation, and I will leave it as it is, and this is the equation of the equipotential surface, I guess. And there is a plane. This equation suggests there is a plane. You should the equipotential surface is related to the plane, and this plane contains the axis of rotation as well. And this is the equation of equipotential surface we were looking, and I think I have solved this problem. Not much satisfactorily, but there was a little information, and I only could reach this part. So, though this problem is complete, there is nothing like the problem is incomplete or something like that. The problem is complete, and this might be the equation of an equipotential surface related to this rotating planet. And that is fine though. Thank you very much for watching.